In this episode, we will talk about chain of model learning for language model. We're seeing these, well, frankly, incredible advancements in what large language models, LLMs, can do.
Absolutely. The progress is stunning.
But, this progress comes with a pretty big bottleneck.
Hmm.
Just the sheer size and complexity of these models. It feels like every time we want more capability, the number of parameters just explodes.
It really does, exponentially sometimes. And that creates these huge training burdens, right? Not to mention making it really difficult to actually deploy them flexibly.
Exactly. It's like trying to improve a library by just making the building bigger and bigger without really thinking about how the books are organized or how people can actually find what they need.
That's a great analogy. Yeah, the current way we scale often means training these massive models practically from scratch whenever we want an upgrade.
Right.
Imagine if learning to drive a truck meant you had to completely forget how to ride a bicycle. Like, starting from absolute zero again. Human learning just doesn't work like that. It's incremental.
Yeah, we build on things.
Exactly, we build. But a lot of current LLM scaling, it just lacks that efficient step-by-step adaptability.
Okay, so this is why today we're doing a deep dive into a really interesting new idea called chain of model learning, or CoM. Our sources suggest this could be a fundamentally, well, different way to build and scale these language tools.
Yeah, it's a fascinating approach. At its heart, chain of model learning introduces this idea of embedding causal relationships directly into the hidden states of each layer, and these are arranged in a kind of chain-like structure.
Okay, that sounds a bit abstract, maybe.
It might sound abstract, but this shift in architecture promises to make training, well, potentially much more efficient. And it offers a new level of flexibility when you actually go to use the models during inference.
So back to your library analogy.
Right. It's like designing our library with specialized sections that actually build upon each other, so you can easily expand, say, the science section without having to tear down and rebuild the whole library.
Okay, I like that. Let's break this down then. The first key concept we need to grasp is chain of representation, or CORE.
Right. Core.
So instead of thinking of the information inside each layer of the network as just one big blob, CORE suggests we can see it as a collection of smaller, connected pieces. I call these chains. And these chains exist at the level of the hidden dimensions within the network itself.
Yeah, think of it like this. You have a representation, maybe a vector of numbers in a high-dimensional space. Chain of representation lets you conceptually break it down into, say, smaller vectors. These are your sub-representations, or chains.
Good.
Each chain has its own size, its own dimensionality. But if you add up the dimensions of all the individual chains, you get back the original total dimension of the representation.
So each chain carries like a piece of the puzzle. And here's the crucial bit, right? If you only look at the first I chains, say the first 2 out of 5, you're essentially looking at a representation at a specific scale, scale I. And the amount of information, the detail at that scale, is just the combined size of those first I chains.
Exactly. So a single representation can hold information at multiple levels of granularity all at once, which is pretty neat.
And importantly, if you just have one chain, if n equals 1.
Then it's just the standard representation we're used to. Core becomes the original thing.
Yeah, the paper we looked at has a helpful diagram for this, figure 1. It shows an example with 3 chains, and you can see how combining them gives different levels of detail.
Okay, so that idea of chain of representation, that naturally leads us to the next step. Chain of layer, or CoL.
Right, so a layer in a neural network, it takes an input, does some math on it using its learned parameters, and produces an output.
Standard stuff.
Standard stuff. Now, for a layer to be a chain of layer, or CoL, both its input and its output need to be describable using this chain of representation concept, let's say with n chains each.
Okay, input and output are both chained. But there's a critical condition. Each output chain, let's call it U sub sub, must only depend on the input chains from 1 up to I. So x sub 1 sub, x sub 2 sub, x sub sub.
Ah, okay, so there's a strict order. Information only flows forward through the chains. U sub 3 sub can depend on x sub 1 sub, x sub 2 sub, and x sub 3 sub, but not on x sub 4 sub or x sub 5 sub.
Precisely. That introduces this vital causal relationship. It's sequential through the chain.
It's like links in a chain, yeah.
Yeah.
Each link only gets influenced by the ones before it. And this cool design, the paper says, has 3 key benefits: generality, causality, and compositionality. Let's unpack those.
Okay, starting with generality. What's really interesting here is that any standard neural network layer we use today, like a linear layer or an attention layer, can actually be seen as a special case of a chain of layer.
How so?
It's just the case where the number of chains n is equal to 1.
Ah, right. If there's only one chain, the rule that output chain E sub 1 sub depends only on input chains up to X sub 1 sub is trivially true.
Exactly. So causal isn't some completely alien concept. It's more like a framework that generalizes what we already do. And it allows us to gradually increase a layer's complexity, its dimensionality, simply by adding more of these interconnected chains.
Okay, that's generality. Now, causality. We touched on this. The output chain, E sub E sub, only depends on the preceding input chain's X sub E sub.
Right. And the paper formalizes this. They call it Corollary 2.2. It essentially says that the layer's internal parameters, its weights and biases, can be kind of partitioned into undistinct sets. The ith set of parameters is responsible for computing the I output chain, X sub E sub, and crucially, it only needs access to the first I input chains, X sub E sub.
And that's where the efficiency gain comes in, potentially.
That's a big part of it. If you only need to compute the output up to scale I, you only need to activate the first I input chains and use the corresponding first I sets of parameters. You avoid doing unnecessary work for the later chains.
That makes sense. And the third property, compositionality.
Compositionality. Also super important for building deep models. Corollary 2.3 shows that if you have two layers, say sub 1 sub and a sub 2 sub, and both of them follow the chain of layer rules, and you stack them, so you compute sub 1 sub x, the resulting combined operation also satisfies the chain of layer property.
Okay, so you can stack them like Lego bricks, and the whole tower still has this chained causal structure.
Exactly. That's vital. It means we can build deep neural networks using these co-layers, and the entire network will maintain these nice properties of chained representations and causal dependencies.
All right, so we've got information represented as chains, ARICO, and layers that process these chains causally. There you are. It seems logical that this leads us to the overall concept, chain of model, or COM.
Precisely. The researchers define a chain of model, or COM, quite simply. It's any neural network where every single layer conforms to that chain of layer property we just discussed.
So if all the layers are co, the whole model is COM.
That's it. And because each layer has those properties of generality and causality,
The model gets them too.
exactly, the whole model inherits them. So just like a single layer, any existing model, like a standard transformer, can be viewed as a COM where the number of chains, n, is just 1.
But the real power comes when n is greater than 1.
That's where the innovation lies. A COM can inherently integrate multiple submodels within the single larger structure. Each submodel corresponds to using only the first I chains.
So you get different scales of capability baked into one model.
Right, and this opens up really exciting possibilities. You can scale up models by adding chains, building on previous capabilities rather than starting over. It offers much greater extensibility and flexibility for these huge foundation models everyone is building.
Okay, so now let's connect this COM idea specifically to language models. The researchers developed the chain of language model, or CoLM.
Yeah, CoLM is essentially taking the COM concept and applying it specifically to the transformer architecture. As you know, the transformer is the backbone of most state-of-the-art LLMs today.
So they went through the standard transformer layers, the attention, the feed-forward networks, and adapted each one to follow these chain of layer principles.
Exactly. Each layer in a CoLM now operates on these chain representations, processing them with that built-in causality.
And the paper highlights this idea of multi-scale training in a single forward pass. What does that mean in practice?
It means that as the data flows through the model during training, the model is simultaneously learning useful representations at different levels of detail, corresponding to the different chain scales, like scale 1, scale 2, up to scale n.
Okay, so it learns to be good at different resolutions at the same time.
That's a good way to put it. And then after training, you can leverage this. You can choose to activate only the first I chains during inference. This gives you multiple submodels of varying sizes and capabilities from just one trained artifact. They call this elastic inference.
Elastic inference, I like that. It's like having a model with a dimmer switch. You can dial it up for maximum power or dial it down for efficiency.
Precisely. And it allows you to scale up your language models by just adding more chains later on. Crucially, when you add a new chain, say chain n+1, the model retains all the knowledge and abilities it had with the first n chains.
So you're truly building on top, not retraining from scratch. That seems like a huge advantage.
It really could be.
Now, they also introduced a refinement called CoLM, which adds a key value sharing mechanism, KV sharing. Can you walk us through that?
Right, CoLM. So in the standard transformer attention mechanism, you compute three things from the input: queries, Q, keys, K, and values V. The queries interact with the keys to figure out which values, parts of the input, are most important.
Got it.
CoLM error changes this. It computes all the T's and values only within the very first chain, the smallest scale representation in each attention layer.
Only in the first chain. Wow.
Only in the first chain. And then these keys and values, computed from just chain 1, are shared and used by all the subsequent chains, chain 2, chain 3, etc., within that same attention layer when they compute their attention outputs.
Okay, so the fundamental context, the K and V, comes from the most basic representation, chain 1, but the queries from the later, potentially more complex chains still use that shared context.
Exactly. It's like the foundational understanding of what's being talked about is established by the first chain, and the higher chains refine their focus, queries, based on that shared foundation.
What happens if the first chain is like really small dimensionally, but the later chains have lots of query heads?
Good question. The paper mentions that if the number of keys and values produced by the first chain is smaller than the number of query heads in the later chains, they simply repeat the keys and values. It's a technique similar to what's used in grouped query attention, GQA, which is another way people try to make attention more efficient.
Okay, so they handled that. What's the big benefit of this KV sharing in CoLM?
There are a couple of major benefits. First, it allows for really seamless and efficient switching between different scales or sizes of the LLM derived from the CoLM error model. You don't need to recompute the keys and values every time you switch scales because they all rely on the first chain's KVs anyway.
Ah, that saves a lot of computation, especially for the context.
A huge amount. And that directly leads to the second benefit, accelerating the pre-filling stage of generation.
Pre-filling, that's processing the initial prompt, right, before the model starts generating new text.
Exactly. It's where the model computes the keys and values for the entire input context. Since CoLM error only needs to do this computation for the much smaller first chain, the pre-fill stage can be significantly faster, especially for very long prompts.
Wow, okay, so faster startup for generation, especially with long context. And the researchers believe this KV sharing approach is novel.
Yeah, they state that, to their knowledge, CoLM error is a new way to achieve this kind of dynamic scalability and pre-filling efficiency.
Okay, let's dig into the nitty-gritty now. How do they actually adapt the standard transformer building blocks, starting with the basic linear layer?
Right, the chain of linear layer. So a standard linear layer is just y, wx plus b matrix multiplication and adding a bias.
Yep.
To make it a chain of layer, they introduce this chain hyperparameter C. It's basically a set of numbers like C sub 1 sub, C sub 2 sub, C sub sub that determine the relative size or proportion of the total dimension that each chain gets for both the input X and the output Y.
So C tells you how to slice up the input and output vectors into these chains.
Exactly. It defines the dimensions D sub B sub for each chain X sub B sub and U sub B sub. Then the actual computation, as shown in their equation 1, is that the overall output Y is formed by concatenating the individual chain outputs U sub B sub. And each E sub B sub is calculated by applying a specific weight matrix Y sub B sub and bias sub B sub, but critically, the input it uses is the concatenation of all input chains up to I, that's X sub A sub.
Y sub B sub times X sub B sub plus sub B sub.
Got it.
That structure enforces the KL causality.
Precisely. And again, if you set N1, so C just has one element, this whole thing mathematically collapses back into a standard linear layer. Figure 2 in the paper shows a nice comparison.
And they mentioned using a special blockwise sparse kernel for efficiency.
Yeah, that's an implementation detail for large-scale training. It helps manage the computations and memory access more efficiently when dealing with these structured, somewhat sparse weight matrices in a distributed setting. It's detailed more in the appendix.
Okay, linear layers covered. What about the attention mechanism? Multi-head attention? Or MHA? That seems trickier.
It is a bit trickier. The most obvious first step would be to just replace all the linear layers inside the MHA, the ones that create the Q, K, V, and the final output projection with these chain of linear layers we just discussed.
Makes sense, but they ran into a snag.
They did. The problem is the dot product attention calculation itself. Inside each attention head, you're comparing queries and keys. If a single head was processing information that came from multiple different chains, because maybe the Q, K, V projections mix them, then the attention scores would blend information across different scales.
Violating the CoL principle, that output chain only depends on input chains up to I.
Exactly. You'd lose that clean separation of scales within a single head.
So what was their solution?
A rather elegant one. They constrained the chain hyperparameter C for the attention layer. Specifically, they required that the sum of the chain ratios in C must equal the total number of attention heads. Ouch.
So if you have 32 heads, the sum of the sub values must be 32.
Right. And what this means is that each value sub now represents the exact number of attention heads allocated specifically to process the ith chain.
Okay, so chain 1 might get the first 16 heads. Chain 2 gets the next 16 heads, for example, if C16, 16. Each head works entirely within one scale.
Precisely. This ensures each head focuses on single-scale information, preserving the CoLM properties. They call this modified mechanism chain of attention. Figure 3 in the paper contrasts standard MHA and chain of attention visually.
Clever. Okay, what about the feed-forward network, the FFN, that usually follows the attention layer?
Similar strategy there. To make the FFN compliant with CoLM, they replace its internal linear layers with chain of linear layers. And crucially, they use the exact same chain hyperparameter C that was used for the chain of attention in that same overall transformer block.
Consistency is key, so the chain structure flows from attention through the FFN.
Exactly. It maintains the chain of representation throughout the layer.
And normalization layers, like layer norm.
That's simpler. They just apply the normalization function independently to each chain. So if you have n chains, you effectively do n smaller normalizations in parallel. Figure 4 shows this.
Does that have any side benefits?
It might actually improve training efficiency in distributed settings. Standard layer norm often requires communication across all dimensions, an all reduce operation. Normalizing per chain reduces the scope of that communication.
Interesting. Okay, last component. The embedding layer at the very beginning.
The embedding layer itself, the big table lookup, isn't really modified during training. But when you want to use the model at a specific scale I, you only take the first part of the resulting embedding vector, the dimensions corresponding to the first I chains.
So you just slice the embedding vector according to the scale you need?
Exactly. The appendix, A6.4, gives a bit more detail on that.
Got it. Let's circle back quickly to that KV sharing in CoLM. You said in standard chain of attention, each chain would have its own keys and values.
Yes, without the KV sharing mechanism, chain I's attention heads would compute and use KVs derived only from sub. This keeps the scales separate.
But CoLM breaks that separation for KVs.
For KVs only, yes. It computes all keys and values using only the input from the first chain, X1 and then shares those same KVs with all the other chains, chains 2 to n.
And you mentioned repeating KVs if needed, like GQA.
Right. If chain 1 produces fewer KV heads than the number of query heads in, say, chain I, those chain 1 KVs get duplicated to match the required number for the attention calculation in chain I. Figure 3C and Figure 9 illustrate this KV sharing setup.
And just to confirm, this still meets the formal KV criteria.
Yes, because the output of chain I sub, while influenced by queries from X ultimately depends on keys and values derived only from X1. Since X1 is a subset of X sub, the causality rule holds. It's a slightly different information flow, but still compliant.
Okay, that's clear now. How do they actually train these models? What's the objective function?
Primarily, they use the standard cross-entropy loss, which is typical for language modeling. You try to predict the next word in a sequence.
Makes sense.
But to really encourage the model to learn well at all the different scales and enable that elastic inference capability, they also introduce a multi-chain cross-entropy loss.
How does that work?
Instead of just one loss calculated at the end using all chains, you calculate a separate loss for each scale I. Loss sub is computed using only the output derived from the first I chains and a corresponding slice of the final classification layer's weights.
So you're explicitly teaching the model to predict, well, using just chain 1, then using chains 1 and 2, then chains 1, 2, and 3, and so on.
Exactly. You're training all the submodels simultaneously.
Does calculating all those losses add much overhead?
It adds some, yes. While the underlying logic computations can often be shared efficiently, calculating multiple loss values does take extra time.
So how do they manage that in practice?
Their strategy is typically to start by pre-training the CoLM model using just the standard single cross-entropy loss calculated using all chains. This gets the model into a good state relatively quickly. Then they follow up with a fine-tuning phase where they switch to using the multi-chain cross-entropy loss. This refines the model's ability to perform well at each individual scale.
Okay, pre-train broadly, then fine-tune for multi-scale performance. That sounds practical.
Yeah, it seems like a reasonable trade-off.
All right, let's talk results. Did it actually work? What did the experiments show?
They ran quite a few experiments. For pre-training, they used the Slim-Pajama dataset, huge dataset, 600 billion tokens. They used the LAME2 tokenizer.
Standard setup for large models.
Pretty standard. Trained on 32 NVIDIA A100 GPUs, used fully sharded data parallel version 2, FSDP2. B, float 16 precision, Fourier-96 sequence length, Atom W optimizer, typical learning rate, trained for about 50K steps, which is around 200 billion tokens seen.
Okay, and what did they compare?
They set up a baseline similar to a LeMMA 3.21b model, 1 billion parameters, which is essentially a CoLM with just one chain, C32. Then they compared this to CoLM models with roughly the same total parameter count but split into chains, C1616 and C8888. They tested these on common sense reasoning tasks, zero shot.
How did CoLM stack up?
Table 1 shows the results. The CoLM models performed comparably to the strong baseline. Interestingly, the CoLM Air variant, the one with KV sharing, did perform slightly lower than the standard CoLM without KV sharing. That's kind of expected, maybe, given the constraint of sharing KVs from only a first chain.
A trade-off for the flexibility and speed benefit?
Exactly. But even with that slight dip, both CoLM variants were generally on par with the baseline, and the 1616 setup seemed generally a bit better than the 88881 in their tests.
So comparable performance, but with the added CoM benefits, that sounds promising. What about that chain expansion idea?
Right, chain expansion. This is where they take an existing pre-trained model and treat it as the first chain, then add new chains on top. It's like progressive learning for transformers.
Building outwards.
Exactly. They tested this using a smaller, tiny llama model and the LeMMA 3.21b model as starting points, chain 1. They added a second chain, size C28, which added about 0.8 billion parameters. They initialized the new classification head for the second scale to zeros, and importantly, they froze the weights of the original first chain.
So only the new chain learns.
Only the new chain and its connection weights learn during this expansion phase. They trained these expanded models for 20K steps. Table 2 shows the results clear improvements over the original baselines after adding and training the second chain. It demonstrates you can effectively grow capability this way.
That's pretty cool. Incremental upgrades. What about the elastic inference?
They showed that too. By training a CoLM Air model 1616 config, using that multi-chain loss we discussed, they could indeed create multiple submodels within one network. They froze the main transformer layers and just trained the classification heads for each scale.
So the core is shared, just different output layers.
In that specific experiment, yes. Table 3 clearly shows you can activate just the first chain, scale 1, or both chains, scale 2, to get models with different parameter counts and different performance levels, all from the single trained artifact.
So you train once, deploy many ways.
Exactly. That's the promise of elastic inference.
And the pre-filling speed up. Was it significant?
Yeah, oh yeah. They showed substantial speedups with CoLM Air, especially for long sequences. Because KVs are only computed in chain 1, the initial prompt processing is much faster. Figure 5 and tables 9-12 in the appendix have detailed numbers for 1B and 8B parameter models, testing context lengths from 2K all the way up to 1 million tokens.
1 million tokens. And the speed up.
For 1M tokens, using the 1616 CoLM Air was about 1.6x faster in pre-filling, and the 8888 config was about 3.0x faster compared to the baseline.
3 times faster pre-fill for 1 million tokens is significant.
Very significant. And they also showed that combining CoLM Air with another technique called inference could push the speed up to, like, 27s in some cases. They suggest this makes it really suitable for architectures that split pre-fill and decoding work, like PD disaggregation.
Wow. Okay, one more experimental piece. Chain tuning.
Right. This leverages the causal structure. The idea is you can fine-tune a CoLM model on a new task by only training the later chains while keeping the earlier foundational chains frozen.
Why would you do that?
2 main reasons. Reduces the cost of fine-tuning, fewer parameters to update, and potentially helps prevent catastrophic forgetting because the core knowledge in the early chains remains untouched.
Makes sense. Preserve the base, adapt the specialized parts.
Exactly. They demonstrated this by taking their expanded 2-chain models and fine-tuning them on the GLUE benchmark tasks, but only updating the weights of the second chain. Table 4 shows performance boosts, even though they only fine-tuned about 42% of the total parameters. They also suggest this is compatible with methods like LORO, low-rank adaptation, for even more parameter-efficient tuning.
So CoM seems to enable more efficient scaling, inference, and fine-tuning.
That's the picture they paint, yes.
How does this fit into the broader landscape of model architectures?
They position CoM as a kind of meta-architecture for scaling. It's orthogonal, meaning independent, of the specific base network like Transformer, Mamba, or RWKV. You could potentially apply CoM principles on top of different base architectures.
So it's not replacing the transformer, it's a way to organize and scale it.
Or other architectures, yes. They contrast it with just making models bigger, dense scaling, or using mixture of experts, MoE. CoM is different because it integrates capabilities across scales sequentially and leverages that inherited knowledge, whereas MoE uses parallel experts.
Okay, and how does the elastic inference compare to other techniques?
They compare it to things like once-for-all or nested architectures, arguing CoM is particularly efficient due to its built-in causal dependencies. They also connect it to continual learning and progressive neural networks, PNNs, saying CoM adapts those ideas for width upscaling and transformers, preserving knowledge better than maybe some depth upscaling approaches.
Interesting connections. The appendix also had some discussion points, right? Like applying this to model depth instead of width.
Yeah, they addressed that. They acknowledged the interest, but said their current work focuses on width, dimensionality. They tried some preliminary experiments applying CoM ideas to layers, like using intermediate layers as submodels, and sharing KVs from lower layers, but saw performance degradation.
Why?
They suspect depth is really crucial for learning high-level abstract features, and just using lower-level states wasn't enough. Plus, managing KV caches efficiently when dynamically skipping layers gets complicated. So for now, CoM is primarily about width scaling, though combining width and depth is future work.
Okay. And they also clarified the difference between CoM and MoE.
Yes, quite explicitly. Table 14 contrasts them. MoE, parallel experts, similar capabilities, sparse activation, router picks experts, CoM sequential, nested experts, chains, progressively stronger capabilities, nested activation, chain I uses output of I1. They see them as fundamentally different and potentially complementary. You could maybe even combine them in the future.
Orthogonal ideas again. And when should people actually use CoM? Is it for every model?
Their take is that CoM is really an optimization for scaling large models. It makes most sense when you're already operating at a scale where scaling laws apply, bigger is better, and the base model has good generalization. For smaller models, the added complexity of CoM might not be worth it if capacity isn't the main bottleneck.
So it's a tool for the big league models.
Seems to be the primary target, yeah.
They also mentioned limitations, right? Infrastructure challenge.
It did. While chain of linear layers work okay with data, pipeline, and context parallelism, they're less of a natural fit for tensor parallelism, at least with naive implementations.
Why is that?
It can increase the communication needed between GPUs, more all-reduce operations, and complicate data access because of the structured, block-wise nature of the computations. Their specialized sparse kernel helps, but they admit truly optimal tensor parallelism for CoM might need new strategies, which is future work.
Okay, so distributed training needs some thought. Any other limitations?
The other main one they highlighted is the design of that crucial first chain, especially in column air, where it computes all the KVs. How big should it be? What's the optimal configuration to make sure it captures enough foundational understanding but is still efficient?
A balancing act.
Exactly. Finding that sweet spot needs more research, they say, which is hard because it involves large-scale experiments. So optimizing that first chain is still an open question.
Okay, so wrapping up this deep dive, chain of model learning really does seem like a potentially powerful new direction for building these massive language models.
Yeah, the key takeaways seem to be this more efficient incremental scaling, the flexibility you get from elastic inference, those significant pre-filling speedups with CoLM air, and maybe even more efficient fine-tuning with chain tuning.
It offers a compelling alternative path, moving beyond just making monolithic models bigger and bigger. It addresses some of the inherent headaches with current scaling strategies.
It certainly suggests a way towards foundation models that could be not just more powerful, but also more adaptable and, importantly, more resource efficient to train and deploy.
This deep dive, I think, really gave us a glimpse into how future language models might be built differently, focusing on efficiency and adaptability right from the architectural level.
Indeed. It's a shift in perspective.
And it leaves us with a final thought for you, our listener, to maybe chew on. What are the implications if AI models could dynamically adjust their own complexity? Think about real-world applications where a model could seamlessly scale its capabilities up or down, depending on the task or the available resources.
Right. How might this idea of nested capabilities, where one AI embodies multiple levels of understanding, how might that change how we interact with technology, how we integrate AI into, well, everything?
Something to think about. We definitely encourage you to check out the research paper itself. We'll link it in the notes. And keep an eye out for the open source code when it's released. that's bound to spark even more work in this really exciting area.